Halbach array generator voltage. In this synchronous generator, the pavement magnets on the rotor are arranged in a Halbach array, which should produce the higher flux density in the air gap. Our task is to find the electromotive force in the stator winding. There is no current in the stator winding, so instead of the motion problem, I can simulate a set of DC magnetic problems with different rotor position. I'm going to measure the flux linked with the phase winding of the stator. And the electromotive force is the derivative of the flux with respect to time. I can replace the derivative with rate of change, and instead of time increment, I will have the angle increment. This part will be done in Excel, and in QuickField I'm going to calculate only the flux versus angle. Okay, let's start QuickField now. In QuickField, I create a new problem, generator. Next. Problem type is magnetostatics. Length units are millimeters, and the axial length of the generator is 50 millimeters. Finish. On the left you can see the problem pane, and on the right is the geometry model editor window. You can draw the geometry model here, or you can input the geometry model from the AutoCAD.xf file. I already have the drawing prepared in the CAD system, so I will import the file. And here is the model. Here you can recognize the stator, the rotor parts, the pavement magnets, the shaft. Let's assign labels. Through labels you can explain the geometric object's meaning and provide physical properties. Switch to Select Object mode. Click the object to select and type in the label name here. This is stator. Okay, click here. This is rotor. This is shaft. Now let's zoom in. Switch to select mode. Click here. This is air. Okay, and these are pavement magnets. Pavement magnets are made of the same material, but the magnetization direction varies, so we should assign different labels. Let's open the picture. Okay, this pavement magnet is magnetized up, so I give it label pavement magnet plus 90 degrees. This pavement magnet is magnetized to the left. I give it label pavement magnet plus 180 degrees. This pavement magnet is magnetized down. Pavement magnet minus 90. And this pavement magnet is magnetized to the right. Pavement magnet plus 0 degrees. Okay, this pavement magnet is magnetized to the right and up. 45 degrees. Pavement magnet plus 45. This pavement magnet is magnetized to the right and down. Minus 45. Pavement magnet minus 45. This pavement magnet is magnetized up and left. 135 degrees. And this is pavement magnet minus 135. This pavement magnet magnetization direction is in between 0 and 45, in the middle. So it is plus 22.5. And this would be minus 22.5. And for this pavement magnet, the magnetization direction is between 45 and 90. which is 67.5. Permanent magnet plus 67.5. And this would be permanent magnet minus 67.5. Okay, this permanent magnet magnetization direction is in between 180 and 135. So it is permanent magnet plus 157.5, and this one would be permanent magnet minus 157.5. Now this permanent magnet magnetization direction is in between 90 degrees and 135 degrees. Permanent magnet plus 112.5. And for this permanent magnet I assign label permanent magnet minus 112.5. Now let's assign labels to the stator winding. 4 half slots belong to the phase A+. Next 4 half slots belong to the phase C-. Next 4 half slots belong to the phase B+. Next 4 half slots belong to the phase A-. Next 4 half slots belong to the phase C+, and next 4 half slots belong to the phase B-. And then it repeats. We have 4 poles. Also, I will assign label to the external boundary. Switch to Select Objects mode, click to select, and hold the Ctrl button pressed to select several objects at the same time. External. Now let's assign properties for these labels. Double-click the label name in the tree. Relative magnetic permeability of the air is 1. Okay. In this experiment, there is no electric current in the stator winding, so for all these blocks, I specify only the permeability of copper, which is 1. For permanent magnets, I should specify permeability, which is 1, the coercive force magnitude, which is 730 kiloamperes per meter, and the direction. Thanks to proper labeling, it's easy. This permanent magnet direction is 0. I will copy this. Okay. For this permanent magnet, same magnitude of the coercive force, but the direction is 112.5. Okay. Now that's all for permanent magnets. The rotor is made of steel and its magnetic permeability is a nonlinear function. I should provide the BH curve data here. Here is the file with the dependency. I simply select, copy, and paste the data here. And here you can see the BH curve. Close, OK. And the same steel is used to make the stator. So I use the same BH curve data here. The shaft magnetic permeability is 1. That is all for block levels. The magnetic field is contained within the electrical machine. There is no magnetic flux going outside. So for the external boundary, I specify 0 magnetic potential. Okay, the geometry model and material properties are ready. Before I can run the analysis, I should build the finite element mesh. Just press this button and the mesh will be generated. Now save all problem files and solve the problem. The problem is solved. Now let's take a look at the results. Here you can see the magnetic field lines. This magnetic flux is produced by the permanent magnets on the rotor, and indeed you can see there are 4 poles. I can adjust the field picture and switch on the vectors of the flux density. So the magnetic field goes out here and then goes back in the rotor here. So this is the north pole, this is the south pole, north and south. Let's calculate the flux linkage with the stator winding. I'm going to use the contour tool. Click here to select the half slot, open the integral calculator, and this is the flux linkage per one turn. And the flux linkage in this conductor is another value. So if I will rotate the rotor, the flux linkage will change. First it will be this value, then it will be this value, then it will be this value, and so on. So I can measure the flux linkage in each slot and get the flux linkage versus rotor position dependence. Let's do it. I will start with this slot. Let's copy the values and put them in Excel. These are the data. This is the flux linkage of the top of the slot. I might need also the flux linkage of the bottom of the slot. But for now that's enough. Let's see what we have here. Let's make the plot. There are few points on this curve. Still, I can see that the flux versus rotor position dependency has a sinusoidal shape. Okay, the alternative way to get this dependency is actually to modify the geometry model, put the rotor in different positions, simulate a set of problems, and measure the flux linkage. This way we can get much more points on the curve, because I can rotate by the small angle. It could be a tedious task. Luckily, there is a way to automate. You can use the label mover tool. In label mover, I specify the base problem name, which is generator PBM. Next, I specify values to measure. I would like to measure the flux linkage with a phase winding. So for each half slot, I would like to measure flux linkage. Add this value, add this value, B plus, B minus, C plus, C minus. Close. Next, I should specify what I'm going to change in the geometry model. Steps, record steps. Well, I can rotate the rotor. But if I will rotate the rotor with permanent magnets, I should also correct the direction, the magnetization direction of the permanent magnets. So I'd better keep the rotor motionless and rotate the stator. So in label mode, I'm going to rotate the stator by 1 degree. Add step. Now you see the stator was rotated by 1 degree. And I'm going to repeat this step 180 times. Okay. Everything is ready to get the results. I have the base problem, I have specified the values to measure, I have specified the steps to perform. Get results. Label generates a set of QuickField problems with different stator position. Then these problems will be simulated, the flux linked will be measured and stored here in the table. Okay, you see 180 problems were generated. Now the problems will be solved. On computers with multi-core processors, LabelMover can open and simulate several problems simultaneously, which is much faster than solving problem one by one in series. It took about 30 minutes to simulate problems, and here you can see the results in the table. Flux linked as a function of the stator position. We can take a look at the plot. This is for the phase A minus, A plus, B minus, B plus, C minus, C plus. Let's save this file. And let's copy all the data for post-processing in Excel. Select all, copy. This is our Excel file. And I paste it here. This is angle. This is A minus, A plus, B minus, B plus, C minus, C plus, and this is the flux linkage per one turn. Now let's calculate the electromotive force. Electromotive force is a derivative of the flux linkage with respect to time. Let's replace the derivative with a ratio of the flux linkage increment to the time increment. Flux 2 minus flux 1 divided by the time increment. Okay. Now, what time is required to rotate the rotor by 1 degree? The rotation speed is 750 revolutions per meter. So it is divided by 60, 12.5 revolutions per second. There are 360 degrees in a circle, so it would be 4,500 degrees per second. And to rotate for 1 degree, I need the time reciprocal to this value. This is the time increment. Okay. Now let's calculate the electromotive force. I copy this here. Now this is the electromotive force. Let's give it another color. And now I should find the difference of the flux values, this value minus this value, and divide this difference by the time increment, 0.000. Okay, and I can copy the equation and use it in other cells. Now let me show you what we have. We have conductor A minus and we have the conductor A plus. These conductors are connected here to make a loop, and these go to the terminals. This is A minus, this is A plus, and the electromotive force direction is here. I can redraw it like this. Electromotive force direction here and here. Conductors are connected here, and these go to terminals. This is A minus, this is A plus. So in order to find the voltage on the terminals, I should find the difference in the electromotive forces. And you should remember there are many turns in the coil. So I should multiply this by the number of turns, which is 90. Okay. That would be another table. This would be the voltages. And this would be A plus minus A minus. This would be B plus minus B minus. And this would be C plus minus C minus. Okay. A plus electromotive force minus A minus electromotive force, and remember to multiply by the number of turns. And for the B plus B minus coil, B plus minus B minus, and multiply by the number of turns. And for the C plus minus C minus, and multiply by the number of turns. And here I'm going to put the time. Here the time is 0, and here the time is this value plus the time increment. Okay. Copy, paste it here. Now let's copy this and use for entire table. Okay, now let's make a plot and see what we have. And here are the voltages that you can measure on the terminals for the phase A, for the phase B, and for the phase C. The dependencies look sinusoidal, but there are also high-order harmonics. Let's find the magnitude of the unity harmonic. I'm going to use the pre-tool that you can find in the Downloads pre-tools section on our website. It is called Harmonic Analysis. Here I should put the data in this field, time and voltage. Okay, let's do the analysis for the phase A. Copy the data and paste it here. Run the analysis. Unity harmonic magnitude is almost 16 volts. And there are also high orthoharmonics. Let's calculate the harmonics content. For example, I would like to calculate first 20 harmonics. Now you see the trend line and the input are the same. So I have all the required harmonics calculated. The unity harmonic is 16. And we have 9th harmonic, which is 0.5 volts. And the total harmonic distortion is 3%. If you search for the Halbach array generator on our website, you will find the example page. Here you can read about problem setup, browse the solution section, take a look at the result pictures, and download the simulation files. Simulation files may be opened and the results may be viewed using any QuickField edition, including QuickField Student Edition, that you can download from our website for free.